Tutorial 2 is about axial loading, and we'll first do a quick revision.
In this chapter, we are concerned with the deformation of a structural member subject to axial loading. By axial loading, it means that the force acting on the object is in the axial direction or longitudinal direction. We'll cover torsion and bending in later chapters. When an object experiences a force, it experiences stresses. In addition, the length will either stretch or compress, depending on whether the stress is in tension or compression respectively. The stress in the object, as we saw in the previous chapter, is P over A. The strain itself for the object is the extension or contraction divided by the original length of the object. Strain itself is dimensionless. Whenever we talk about stress and strain, we will relate it to the stress-strain curve as you see over here. On this curve, we have stresses on the y-axis and strain on the x-axis. This curve relates the amount of extension or strain to the amount of stress exerted on the object. Both graphs here are for ductile materials. As stress increases, the strain itself will also increase because the material gets elongated. The first part of the stress-strain curve is what we call the elastic range, where the relationship between stress and strain is linear. In this region, the length or dimension of the object will return to the original form after the stress is removed. The maximum stress for which the object or the material exhibits elastic behavior is known as the elastic limit. Beyond this point is the plastic region, where the object will have permanent deformation. It will have permanent deformation after the stress is removed. In the plastic region, there are few things that can happen. The material can yield, where the cross-section remains the same, but the material exhibits plastic deformation. It can go into strain hardening, where the dislocated grains becomes entangled as they move past each other, giving additional friction. Before rupturing, the material will undergo necking, as you can see over here. This is necking, where the weakest regions in the material have its cross-section deformed and string, resulting in necking. Among this behavior of the material, there's a point where the stress is the highest. This itself is what we call the ultimate stress. Next, we have brittle objects, which behaves very differently from ductile materials. For brittle objects, it will only exhibit the linear elastic range, where the object will return to its original form after the stress is removed. At the ultimate stress itself, the object will rupture. It does not exhibit the plastic range. Ductile materials are weak in shear, and brittle materials are weak in tension. This itself we will understand what it means in a later chapter. In the elastic range, we have shown previously that the stress-strain relationship is linear. This relationship is also known as Hooke's law. We can write the stress itself is equals to constant multiplied by the strain. This constant itself is known as the Young's modulus, modulus of elasticity, or elastic modulus. Young's modulus defines the stiffness of the material, which is the amount of stress to deform an object. In the figure here, all the different materials here shows the same stiffness E, because they all exhibit the same behavior in the elastic range. However, their point of breakage is different. How much stress is needed to break an object over here is what we call the strength of the material. Strength itself is affected by alloying, heat treatment, and manufacturing processes, but stiffness itself is not. When we stress an object, the stress itself may not always be constant. The stress itself may be constantly changing or harmonic. At some point in time, the material may undergo what we call fatigue. An object may fail due to fatigue at stress levels significantly below the ultimate stress of the material if it's subjected to a loading of many cycles. There's also a loading that we call the endurance limit. If the repeated cycles of stress are all below this endurance limit, fatigue will not occur, regardless of the number of cycles. This is like taking your paper clip and then repeatedly bending it. If you exert small deformations in the bending cycles, the paper clip will hold in place. But if you exert more deformation in the bending cycles, the paper clip will undergo fatigue and break off. For an object under axial loading, we will want to know what is the amount of deformation. To do so, we can make use of equations we studied previously. Equation 1 here says the extension is equal to strain multiplied by the length. Equation 2 is the Hooke's law. Equation 3 says that the stress is equal to force over area. We substitute equations 2 and 3 into 1 and we arrive at this equation here, which says that the extension due to axial loading is equal to force times length divided by cross-sectional area divided by the Young modulus. If we have multiple loading, we can make use of the principle of superposition where we can sum up the extensions over different sections as given in this equation here. Whenever we stretch an object, it will elongate in the direction that we stretch. In this figure, we have stresses only in the x direction. As such, the elongation in this direction, where the strain in the x direction itself is given by epsilon x equals to sigma x over E. However, when we have material gain in the x direction, there needs to be material loss in other directions. As a result, there will be contraction in the other directions. This means that the strain or change in dimensions in other sections is non-zero. We can define a parameter known as the Poisson ratio, which defines the lateral to axial strain. It gives the ratio of the amount of change in material length in one direction, epsilon y and epsilon z, to the amount of change in material length in the x direction, epsilon x. The negative sign here is to make Poisson ratio positive, because contraction is negative. In this course, we assume material is isotropic so that Poisson ratio is the same in all directions. Example, metals or glass or polymers. This may not be the case for non-isotropic materials such as wood or composites. If instead of having stresses in one direction, we have stresses in all three directions, sigma x, sigma y, and sigma z. If we want to find the strain in the x direction due to the combination of all these stresses, we can make use of the equation over here. The stress in the x direction will cause an extension in the x direction, hence it is positive sigma x over E. The stress in the y direction itself will cause a contraction in the x direction. Same thing, the stress in the z direction will also cause a contraction in the x direction. As such, we have negative Poisson ratio sigma y over E and negative Poisson ratio sigma z over E. Note the signs here, positive for tension, negative for contraction. Correspondingly, we can also find the strain in the y direction and the strain in the z direction subject to a combination of all three stresses in x, y, and z. Next, there is shearing strain. Whenever there's a shearing stress acting on an object, the object itself will deform in a way that layers will slide past each other. As a result, there will be an angle gamma being formed, which we call shear strain. Shear strain itself is given by gamma here and gamma here. It has the units of radians. The relationship between shear stress and shear strain is as such. It is linear. Tau itself is equals to G times gamma, where G is what we call the modulus of rigidity or the shear modulus. If we have an object that is undergoing shear stress and we draw an element on the object, the stresses that is acting on the object itself will exhibit such behavior, where the top and bottom shear stress will cancel out in terms of different directions, left and right will also cancel out. This is such that the object itself is in equilibrium. Now, under this case itself, the forces or the shear stresses, you'll notice that along this diagonal, it will elongate, and along this diagonal, it will contract. If we were to rotate this element by 45 degrees, you'll notice that the stresses itself, which was shear stress, will become normal stress acting on the diagonal inclined surface if it's 45 degrees. On this side, it will undergo tension. On this side, compression. Note that only when the rotation is 45 degrees, then pure shear itself will be converted to pure tension and compression. If it's not 45 degrees, therefore we will have both shear as well as tension and compression acting on the object. In summary, these are the equations you need to know from this chapter. Hooke's law, equation for strain, deformation as a result of the external loads P, as well as Poisson ratio. For objects that are stressed in multiple directions, the strain in one particular direction can be represented as such. We also introduced the shear strain equation, and also the relationship between shear modulus and Young modulus is given here. Let us now look at the tutorial questions. In question 2.19, we have a rod A, B, C that is of different cross-sectional areas. We are told that there are two forces acting on it. Force P itself that is stretching A, B, C, and force Q that is compressing only B, C. We will need to find the values of Q such that the deflection at A is 0, and also to find the corresponding deflection at B. Let us illustrate the deformation process using the diagram here. Originally, the rod is of length LAB plus LBC. The force P will cause ABC to elongate, where the length becomes LAB prime plus LBC prime. The force Q will cause contraction in BC only, such that the length of BC becomes LBC double prime. The final length of the rod, as the question states, is that the deflection at A is 0. As such, the contraction at B here is so that it makes A goes back to its original position. We can write the equation as such, where the initial length LAB plus LBC is equals to the final length LAB prime plus LBC double prime. On the right hand side, LAB prime is equals to LAB plus extension delta AB, and LBC double prime is equals to LBC plus the contraction delta BC. After removing the common terms, we are left with delta AB plus delta BC equals to 0, or in other words, the extension of AB is equals to the contraction of BC. To find Q in part A of the question, we first work on the equations we found earlier, where delta AB plus delta BC equals to 0. Delta AB is the change in length of AB. Given that delta AB equals to PLAB over EA, as well as delta BC is equals to P minus Q, L over EA. The force acting on BC itself will comprise of P and Q, as such you have here. the force acting on AB is only P. Here, we take Q itself to be negative because it is in contraction. Note that the cross-sectional area of AB and BC are different. Working out the expressions over here, where this is cross-sectional area of AB, this is cross-sectional area of BC, substitute all this into this equation, and all the known values for P, as well as E and L over here, we are able to find the unknown Q, and Q itself is equals to 32.8 kilonewtons. For part B, we are asked to find the corresponding deflection at point B. We know from the previous equation here that delta BC equals to negative of delta AB. Hence, we can just make use of the expressions for delta AB, which is this. Substitute in the known expressions or the known parameters. We find that the deflection at B is just 0.0728 millimeters. In this question, we have a rectangular frame ABCD with additional rods that forms an X in the middle. The diameter of the rods are given. The diagonal AC itself has a turnbuckle. When tightened, the turnbuckle pulls both ends closer to each other such that AC itself is in tension. We are told to find the largest allowable tension in AC such that deformation in AB and CD does not exceed 1 mm. In order to find the tension in AC, we will first need to find the force in AC. And the force in AC can be found using the forces in AB or CD, where the deformation criteria are provided over here. We are told that the deformation in AB itself and CD cannot exceed 1 mm. As such, we will first find an expression that relates this deformation to the forces. Let us consider this equation over here, which says that the deformation of CD itself is equals to FL over AE for CD. This deformation for CD, as the question states, cannot exceed 1 mm. As such, we substitute in the values for delta as well as the other terms and make FCD the subject. Subsequently, we find the equation here of the expression here where FCD itself is 117.8 kilonewtons. An observation we can make here for this problem is that all the rods itself are two force members because they are pin-ended and there's no transverse loads. Hence, we can use the methods of joints at point C, where the forces AC and CD meets. Because the rod AC itself is in tension, the direction of force acting on pin C will be known. The forces in BC and CD we'll assume they are in the directions as shown over here. We bring the forces out and form a triangle. They must form a loop such that it is in equilibrium, showing the directions. After which, we are able to solve using the sine rule, where FCD itself divided by sine of 53.1 degrees is equals to FAC sine of 90 degrees. From here, we are able to solve and get FAC equals to 147.3 kilonewtons. Alternatively, we can also use the length, or rather the ratio of the length, to solve for FAC, which is the same as the sine rule. In this question, we have a fabric itself that's undergoing biaxial loading. You can see it as a piece of cloth that's stretched on both sides. The stresses are 120 megapascal in the x direction and 160 megapascal in the z direction. We are given the Young modulus and the Poisson ratio. We are told to find the change in length of sides AB, BC, and AC, which is the diagonal, subject to the stresses. This question involves finding strain due to stresses in multiple directions. As such, we need to make use of the Poisson ratio equation. For part A, we are told to find the strain on sides AB, which is in the x direction. As such, we'll use the equation for strain over here. Sigma y is gone because there's no stress in the y direction. Substitute in known parameters into the equation and we arrive at the strain over here. As the question itself is asking for change in length, therefore we need to multiply the strain by the original length to get the change in length, which is 0.0754 millimeters. We can do the same for the side BC, where the strain itself in the z direction is given by the equation here. As such, substituting in known parameters and you will obtain the strain as such. We then multiply the strain by the original length, which is 0.075, and we get 0.1028 millimeters. For the diagonal length, we cannot just take the Pythagoras theorem of the deflections AB and BC. The reason itself can be observed here. This itself is the original fabric. After it's been stretched, it becomes this form. AC itself, this is the original diagonal, and after being stretched, the new diagonal is of this form. Hence, in order to find out what is the extension in AC, we'll need to take the original AC length as well as the stretched AC length. We then deduct the new AC length with the old AC length and we get the extension, which is 0.122 millimeters. In this question, we have two blocks of rubber here that's of modulus of rigidity of 12 megapascal given. This rubber itself is bonded to two supports by the sides as well as a plate in the middle. We are given the dimension C here, which is 100 mm, and the plate at the center is being pulled out at 40 kilonewtons. We are asked to find the smallest dimension A and B such that the shearing stress in the rubber itself does not exceed 1.4 megapascal and the deflection of the plate is to be at least 5 mm. You can imagine this question as a hamburger. The rubbers here are the meat, the center plate is the center bread, and the top and bottom support is the bread on top and below where you will hold the burger. Because you're not that hungry, therefore you will just want to eat the bread at the center. You'll bite and pull. And then you will bite and pull such that it moves out at least 5 mm. And also you want another condition that the shear stress in this meat or the rubber does not exceed 1.4 megapascal. So the next time when you eat a hamburger, think about mechanics of materials. Let us redraw the question here. Here we have the plate AB, the rubber, and the rigid support. The two criteria are such that the deflection itself of the center plate must be greater than 5 mm. The shear stress must be less than 1.4 megapascal. To solve for this question, we'll need the equation for the shearing stress, which is tau equals to G gamma. If we look at the deflection over here, gamma itself is the shear strain in radians. Gamma can be expressed as tangent gamma equals to delta, which is the amount of deflection, divided by A, which is the thickness of the rubber. Using small angle approximation, we can get gamma equals to delta over A. Substitute this into the expression and we get this form. We then substitute in known parameters from the questions for tau, for g, for delta, and we get A equals to 43 mm. We then look into the shearing stress criteria. For the center plate itself, we know that there is a force P that's trying to pull out, and the plate itself is attached to a rubber on both sides. As such, this forms our double shear problem. The shear stress acting on this plate itself is given by tau equals to P over 2 divided by area because it's a double shear problem. A itself is B times C. Substitute in the known parameters. The only unknown is B, and we obtain 143 mm. This comes to the end of the tutorial.